Welcome back to Polymer Science and Engineering. This is video recording number 8, and I will carry on from where I left off in the previous recording. So in my last recording, we ended off discussing rubber elasticity, and in this recording I will focus on the thermodynamics of rubber elasticity. Before I jump into thermodynamics. If you take a look at the picture that I use to represent an elastomer here in this slide, is actually a slinky toy. So in other words, an elastomer actually behaves like a spring. When you talk about thermodynamics and spring, what comes to mind is how the first and second laws of thermodynamics are used to describe an entropy spring, which is exactly the same way that we can use to describe an elastomer, an ideal elastomer. Now, I'm not going to go straight or go deeply into how we derive this equation at the top, simply because it is a pure thermodynamics exercise. If you are interested in finding how this equation is actually derived, you can refer to page 179 of Rudin's textbook in chapter 4. It shows you how you actually derive this equation from the first and second law of thermodynamics. For me, I'm more interested in how we can use this equation to help us in finding how elastomers, an ideal elastomer, will behave. So what this equation tells us is simply the internal energy contribution to the total force of the elastomer is equivalent to the tensile force acting on the polymer minus the temperature multiplied by the temperature coefficient of tension at constant length L. Now it sounds like a mouthful, but in actual fact it is a very simple and straightforward equation, okay, which is summarized by the orange words on top. The tensile force acting on the polymer F is equals to the internal energy plus entropy, which is what you get in an ideal gas expressed as an entropy spring. Now, in an ideal elastomer, when you stretch these materials, once you release your force, the elastomers will return to its original position. That means the internal energy contribution to total force is equals to 0. And you can express the tensile force acting on the polymer solely based on entropy. And this is in complete analogy to an ideal gas, where the pressure is due only to the entropy contribution. In real life, elastomers behave slightly differently. You have to factor in, now that means that in the internal energy contribution to the force is not equivalent to 0. And this is because when you uncoil your elastomer chains, it also involves overcoming bond rotational energy barriers. In this case, we need to factor in the term Fe, which is the internal energy contribution to total force at constant length and sample volume. Another type of real-life polymer elastomer that we commonly see is the cross-link elastomer. So here we'll take a look at the stress-strain properties of cross-link elastomers. So when you stretch the cross-link elastomers, there will be an increase in length to the unstretched length, and this is called the nominal strain given by epsilon. And sometimes deformation is also expressed as the extension ratio, shown here by lambda. Using lambda and epsilon, if you plug it into statistical mechanical calculations that show that the entropy change is a function of the number of chain segments between the cross-link per unit volume and the Boltzmann's constant and kappa, then you can derive to this equation shown here in the box. Now this equation is valid for small extensions. It predicts the stress strain of elastomers that behave like entropy spring, depending on temperature, density of material, and average weight between crosslinks. Which can be expressed through the term MC. The exact derivation of this equation can be found in Rudin's textbooks on page 182, and as I'm more interested in knowing how to use this equation, I won't go into the exact derivation of this equation here. I will go through the an example of how we can use this equation in one of the hybrid seminars related to this topic. Moving on from elastomers, cross-link elastomers, real-life elastomers, or even ideal elastomers, we will now discuss the topic of polymer viscoelasticity. So in an ideal elastic material, it doesn't exhibit any, no time effects. So when a stress is applied to an ideal elastomer, the body deforms immediately to a strain. This strain is always proportional to the stress and is independent of the rate at which it is applied to a body. And this is similar, and this can be described using Hooke's law, where the stress is a product of the Young's modulus Y multiplied by the strain. Now, for viscoelastic polymers or even elastomers, what we're interested is in the elastic moduli, which is how well or looking at the volume changes as well as the shape change of a specific material as a function of stress and strains. So the elastic moduli can be expressed using this equation, whereby the Poisson's ratio beta is equivalent to half of the product of 1 minus 1 on V multiplied by changes in V due to a change in the strain. When there's no significant volume change, beta is equivalent to 0.5, and this is typical of an ideal rubbery material. As real solids dilate when extended, values of beta can go down to 0.2, and this is characteristic of rigid brittle materials. For isotropic solids, the elastic moduli can be expressed using the second equation shown on the right here, whereby the Young's modulus Y is equivalent to 2 multiplied by the shear modulus G multiplied by 1 plus the Poisson's ratio. When Y on G is equivalent to 3, it is symbolic of an elastomer. Y on G is commonly used to describe permanent deformation. For rigid and brittle materials, Y on G is usually 2.5.